I'm going to start talking, and hopefully things can be sorted out during their first few, 10, 20 minutes of lecturing. This screen is about to go away. I'll put all of that content into this nice Gitter channel, which I am not logged into on this machine, of course. Oh man, that is bad. Whew. Okay. Okay, so while that's happening, so I have downloaded the Git repository, and I have this directory here. I can look at the README to get the instructions on how to set everything up. I'm going to install some packages. I'm going to activate this particular content environment, and I run the Jupyter Notebook. At that, great. Okay. At that point, I have a single notebook, and the rest of the tutorial will be in this one notebook. So, about Skipper. So Skipper works at Civis Analytics. He's also pretty active in the open source community. People may have sort of seen the name Jay Siebold, Skipper Siebold. Works on lots of things, including stats models. This is going to be talk about Dask. Dask is a library for parallel computing in Python. Dask does many things. These particular materials go into Dask's sort of big data collections, a Dask bag, a Dask array, and a Dask data frame, which are large parallel versions of lists, NumPy arrays, and pandas data frames. There is some sample data in here, which is around 50 megabytes. And there's also a bunch of exercises to go through both some toy problems and some more real problems. Skipper's included some fun data sets in here that are actually fairly interesting. So, at a high level, we're going to sort of parallelize NumPy and pandas and Python lists with this sort of lightweight Python library. If you're interested, there's lots of information. If you go to dask.pydata.org, when you have internet, you can get lots more information. There's other tutorials listed there. There's lots of YouTube videos, learning materials, etc. So at its core, Dask is a task scheduler, which means that it has lots of little Python functions that all depend on each other, and it runs those Python functions in parallel. That's sort of the core piece of Dask. On top of that, we've built parallel arrays, parallel data frames, etc. This talk is just going to be just on the high level, just on the parallel arrays and data frame stuff, and not on the core. I'll be giving a talk on Sunday that's more on the core, which is useful in different situations. Oh, man.
Can you make that bigger?
I can. Thank you. If I understand Mac, I can, rather. There we go.
Also, we have a network in the Gitter channel.
What is that network?
C1 covers.
Is there a password?
Yeah, the password is. Yeah.
All right. Just in case people can't get to the Gitter channel. Sorry?
Yes.
Sold 6?
Sold like I bought or sold
Mhm.
a car.
6?
6. / 5 ways.
Like this.
Yeah.
I'll go try that out right now. Okay, this screen is about to go away. Okay, there are some thumb drives in the back. The screen's about to go away. Does everyone have that? Great. There we go. Great. So, for the purpose of this talk, there are 3 collections. There's a large parallel array. There's a large bag, which looks kind of like a PySpark RDD, and there's a large data frame, which is a lot like a pandas data frame. These objects produce task graphs, which are sort of arbitrary collections of Python functions that need to run with dependencies in parallel. And then we can run any of those collections in a variety of schedulers. On a single machine, we can use many threads or many processes, or if we want to, we can use a distributed scheduler. We're going to first talk about Dask array. So one Dask array is composed of many small NumPy arrays arranged into a grid. So these NumPy arrays can be on disk in a large HDF5 file. They can be on a cluster on different machines. And then one logical Dask array will just call a lot of NumPy functions on all those NumPy arrays to produce logical results. So if I wanted to say sum this large array, I would sum all the NumPy arrays and then sum their intermediate sums. Dask array follows most of the NumPy syntax, not all, but a fairly full subset. So we're going to play with Dask array first. This is sort of the most intuitive, also came first. And so if I were to say import NumPy, I might make a NumPy array of the first 25 numbers. Or in Dask array, I could do that same thing, but replacing the NumPy with NP with DA for Dask array. And I provide one more piece of information, which is how I want to break up my large array. So here I'm asking to break up that large array into chunks of size 5. So I'm going to have 5 chunks, each of size 5. Oops. So the object that we get out is a Dask array. We can do normal Python syntax on that. And that produces more Dask arrays. And if we look at what that did, that produced a computational graph of functions we have to call in order to create this result. So for example, if I wanted to say look at x.sum, I would call a range on a bunch of different pieces, then I would call sum on all of those pieces, and I would sum all of those sums. So this is a way of visualizing the computation. Though that computation is stored internally as a bunch of sort of delayed functions, this should look like gobbledygook to you, but the very sort of technical people might want to look at this and see how it's sort of arranging and representing these computations. And then at the end, what we actually care about is actually producing that result. So I can do x dot squared dot sum, and I can get a result out fairly quickly. So this is a very small example, but it's showing how Dask array is composing normal NumPy syntax as a bunch of small NumPy functions coordinated together. Okay. So as an exercise, quick show of hands, who is ready to go with everything right now? Great. Okay.
Your best bet is to get the tutorial materials on a USB stick at this point, and you don't have Dask installed. If you have Anaconda, you actually already have Dask installed. Anaconda comes with Dask, so you don't need you can get through these basic exercises just with an Anaconda installed.
Right.
So what we're going to do is the USB keys are still floating around. I'm going to pull down some Anaconda installs as well. Actually, probably going to go downstairs and see if I have those available on a key.
So if you have Anaconda installed, you could go to this GitHub repository and just download this single notebook.
Yeah.
And that would have enough information for you to do the first part of the class. The second part involves some data. That will be inspections, which is maybe like 20, 30 megabytes. And then the last part is NFS, which is maybe 50 megabytes. So we could pipeline that a little bit. Yeah. So there's a question about this visualize command. So this will only work if you have the GraphViz system library installed on your computer. So if you're on Windows, Mac, or Linux, you need to install GraphViz somehow. That's the GraphViz tool. So like if I'm on Linux, which I am usually, I would do sudo apt get GraphViz. Presumably on Mac there's Brew, and on Windows there's an installer you can go and click on. Okay, so I'm just going to do this first exercise because it's hard to do without materials. So the exercise here is to create an array that has 25 chunks that represents the first 2,500 elements, the first 25 numbers. So in NumPy, I would do numpy.arange 2,500. In Dask, I'm going to switch NumPy to Dask array. And then I want 25 pieces, so each piece is going to be of size 100. So chunks will be a size 100. And we can look at that, and we can look at, maybe we'll visualize that, just to verify that what we did is reasonable. So that looks like roughly 25 calls to arange. So one call to Dask array arange is calling many calls to NumPy arange. If we look up here at the sort of Dask graph, we saw that we sort of called NumPy arange on 0 to 5, then on 10 to 5 to 10, then on 10 to 15, etc. So this is how we're composing one large computation of many small ones. This exercise then asks us actually to take the square root of all the elements. So we call dA dot square root on x. And then just look at the last element. So if we were to print just this, right, so again, saying make this array, take the square root, print out the last element. If I print just this, I actually just get this weird Dask array thing. I actually want to get the result. To get the result of a Dask array computation, or of any Dask computation, you have to add a compute at the end. And this is going to take that lazily executed graph we've built up and actually evaluate all of those functions. In this case, using a thread pool. If I wanted to get maybe every 10th element, I would slice differently. Okay. Just to be a little bit fun, because it's so let's make an array that's maybe two-dimensional. So this one-dimensional stuff is fairly straightforward. We know sort of how to sum up a large array of numbers. It becomes more interesting if we look at maybe a two-dimensional array. So here I'm making a 15 by 15 array, cut up into blocks of size 5 by 5. So I've got sort of 9 blocks arranged in a 3 by 3 grid. Each of those blocks is 5 by 5. And I might, visualize this. And again, you see sort of these 9 blocks. But we can start doing some fun things here, like summing along one dimension. And we start to see some more interesting patterns. You can do this if you have Anaconda. You can walk into a terminal right now and start playing with this code. It doesn't require anything. So it's sort of fun and it's informative to look at different kinds of computations you might do, and what those might look like. So here I'm adding x to its transpose. So I'm making x sort of flipping around, and I'm adding different blocks to each other. So what you see is that on the diagonal, blocks add to themselves, and off the diagonal, they add to their sort of neighboring partners. We can start to go sort of crazy here. We can do a matrix multiply. We can maybe subtract off a mean. Let's take the standard deviation of that. And so we can build these sort of more and more complex computations, all using Dask array. So each of these little circles is actually just a small NumPy computation. And then when we, instead of calling visualize, if we call instead compute, we are sending lots of threads to run through that graph of computations, execute all those NumPy functions, be aware of sort of what dependencies need to be run before others, and produce for us the result. So this is parallel computing. It's still using NumPy under the hood. So it looks like NumPy to the user, but it sort of is a way to coordinate lots of small NumPy arrays to act as a large whole, using all the cores of your computer. It also runs well off disk, so it'll try to garbage collect data in RAM fairly quickly. I'm sort of going to talk materials I usually give when I'm just giving a talk. If people are suddenly ready to do stuff, I will switch back to other things. Quick show of hands again. Who is ready to go? Oh, we're getting that's like 25%. Okay. Quick show of hands. Who is ready to go or is comfortable enough with their neighbor to work with them? So all of the previous hands should also be up. Okay.
So at this level, what we've done is using whatever cores or threads are in our computer to show you that. And where you had 5 chunks, I'm pretty sure you have 4 threads on that Mac. It's taking a fifth and just having it wherever.
Yeah. Yeah. So the question is one of scheduling backends, which is conveniently the next section we're going to talk about. So that's a great question. Yeah. So there's lots of different little circles in here, right? There's 9 circles available up front, and once you finish one of them, some more became available. So the question is, how did all the threads get assigned to all those little Python functions? The answer was with great care. So Dask thinks very, very strongly about what functions it should run, when it should run them. It tries to run computations that let it, release data that was in RAM before, computations that let it do more parallelism in the future. It's an interesting problem. If you come to the talk on Sunday, I'll be giving a talk on sort of more advanced stuff. You'll see lots of interesting visualizations on exactly how those questions are decided. Yeah. Okay. So this used threads by default. So Dask array tends to use a local thread pool, but you don't always want to use threads. You may be using Python code that doesn't work well with threads. Maybe it holds onto the GIL. So you want to use processes instead. There's a big question of whether you use threads or processes. Or you may have a cluster of computers you want to use rather than it's your local laptop. You may have 100 machines, and you want to run a larger computation on those 100 machines. So Dask's ability to create these parallel graphs and Dask's ability to compute these graphs is separated. So, for example, we have this computation. Let's make this fun computation here. Let's just call that y. So we can control the scheduler we use by this get keyword argument to the compute method. And we have a few options. The first option here is actually just the default scheduler, which actually just runs in the standard thread of your interpreter. So there's no parallelism here, but it does let you, enter into the Python debugger. It lets you use normal profiling tools. Sometimes it's nice to not use parallelism. And so here we just ran that same computation, but inside my local thread rather than in parallel. Or I can run this with threads. And by default, we're going to use as many threads or processes as there are logical cores in my computer. That's completely tunable, but that's by default. Let's say we had Python code, pure Python code that held onto the GIL, so it didn't sort of operate well with parallelism and threads. You may have heard of this thing that Python doesn't work well with parallelism inside of a single process. That's definitely not true for NumPy or Pandas code, but it is true for pure Python code. So if you have pure Python code, you may want to use processes instead, and we can do that by again, adding a different keyword argument to this compute method. There's a distributed scheduler as well. You can connect to a cluster in your institution, and it's very simple to run the same computation also on that system. There'll be more of that in Aaron's section of the talk right after this, which doesn't require any data, and there's a cluster set up for you already, so there's no bandwidth issues. But you'll have more time to play with that in the next tutorial. Okay.
Specifically the parallel tutorial after this tutorial.
Yeah, so it's currently 9. At 10:30, there's a separate tutorial that was put together by other people that will have different materials and a different way of delivering data. So, okay, so all those computations we just did were all quite small. They were, on little small arrays. In this next section, we're going to make a larger array of data on our laptop. This is going to make around 4 gigabytes of data, random data, in an HDF5 file on my local hard drive. This is going to take a minute. It's not trivial to write down 4 gigabytes of data, random data, and produce it for a laptop. Once we have this, though, this looks a lot more like a reason you might want to use Dask. Generally speaking, if your data is small, you should continue using NumPy or Pandas or Python lists. But if your data is larger and doesn't fit in RAM, or you want to use many cores, that's really the right place to use Dask. So this is producing just a large array of maybe 1 billion elements into an HDF5 file. HDF5 is a nice way to store numeric data on disk. And what we're going to do then is we're going to think about blocked algorithms. So we might ask the question, okay, if I have these billion numbers on disk, how do I add them up? If I just want to do a simple summation computation. And that's the question you might reasonably be faced with at work. You have a large column of data, you're asked to find the mean of this or the standard deviation of it. You don't have any parallel computing tools, you just have Python. How do you compute the average of a large piece of data that doesn't fit in disk? So what we can do is we can just walk through that array and say million element chunks. That's what we're doing here in just normal pure Python. So this isn't Dask, this is just standard Python. And we're going to walk through this data set. We're going to pull off a slice of size 1 million. So the first million, then the second million, then the third million, etc. We're going to compute the sum of that chunk of data and append it into a list. And then once we're done walking through that array, we're going to compute the sum of all of those sums. So it looks like I've finished creating my random data set. I'm loaded up with the H5Py library, which is a great library for reading HDF5 data. We see it's a 1 billion elements long, so this is inconveniently large. I can go ahead and I can do this for loop, and it will walk through this data set, reading chunks of data, summing them, pulling them back. An interesting challenge would be to think about how you might compute the mean or the standard deviation of a data set like this. So the sum is fairly easy, but it's a bit harder sometimes to think about some of these other more complex computations. Or maybe the mean of all of the positive elements. So if you're sort of thinking, if you sort of want to do some work, it doesn't require any data to play with, it's something you think about. How do I compute the average of all the positive elements using this sort of way of walking through a large data set? With Dask, Dask will do it for you. That's sort of the things Dask does, but it's educational to try to do that yourself, to see the sorts of problems that arise. So we can do the exact same thing that was in this cell. We can do it here. We have this HDF5 data set. We're going to wrap a Dask array around that with this daskarray.fromArray function. And we need to give it the size of chunk that we want to operate with. So look at this HDF5 file. Consider it in million length chunks. And that happens immediately because we haven't done any work. But now we have this nice NumPy-like abstraction over this HDF5 file that we can do all this computation with. So we can, for example, compute the mean. That didn't do anything because, again, it's just producing a lazily evaluated graph. If we actually want to compute the result, we need to call this compute method at the end. Now this is actually doing this work. It's pulling off different chunks of that HDF5 file, it's computing their sums, it's computing more sums, and we get out our answer. That happened in parallel, is very mindful of RAM. If we just want a little bit of data, Dask is also quite smart in just doing a little bit of work. So it's because it sort of is lazy, it can do these things in a more intelligent way. Okay, this is actually going to be an exercise. I'm not going to talk through this one. So use the Dask array random.normal function. This looks just like the NumPy random.normal function, except that it takes an extra chunk argument to make a 20,000 by 20,000 array of values distributed with mean 10 and standard deviation 0.1. The random normal docstring is fairly good. It'll tell you how to do these things. So da.random.normal. So loc is mean, scale is standard deviation. You need to provide a size and also a chunks. So you're asked to break up your 20,000 by 20,000 array into chunks of size 1,000 by 1,000. Then you're going to take the mean of every 100th element along axis 0, or do whatever you want. There's lots of things you can do. After that, we're going to compare performance with Dask array and NumPy and see that we're actually getting some parallelism. Okay, I'm going to stop talking for a while. Are there any general questions about what I've just gone over? Okay. I encourage people who don't have things set up to find a friend. The hands are relatively uniformly distributed across the room, so at least sort of meet a friend and see if you can look around, look over their shoulder. Pair programming is an excellent way to learn. Okay, I'll walk around for a while. Okay, I'm going to get started again, just because we are sort of low on time. People seem to be having an okay time. It's a fun adventure, everyone. So I'm going to blow through a couple things, just so we can get to some of the exercises that have some actual data, which I think will be fun. I'm copying some USB stick, that's new. Great. So there are also solutions here if you want them. So here, we're creating a random normal array, breaking it into chunks, and then computing the mean across an axis, and then taking every 100th element. If you know NumPy syntax, it should look pretty familiar to you. That ran really quickly. It didn't actually compute anything. It just produced for us one of these graphs. If we want to compute it, we can call compute. That's actually going to create lots of NumPy arrays, compute their means, compute every 100th element, etc. That used all of our cores, and it ran in small RAM. There's some nice diagnostics. I'm going to skip that for a moment. Let's do this. So we can do this with NumPy as well, but NumPy has a couple of hindrances. One, it's going to run inside of one thread, so it's going to be fairly slow. And second, we can only do this if we have around 4 gigabytes of RAM on our machine. And I hope this machine does, otherwise problems. So that ran about 16 seconds. And Dask array can do that a bit faster because it's able to do all of the random number generation in parallel, which is the current bottleneck of this computation. So it ran in about 3 seconds. What's sort of nice, actually, you can see, so Dask has some nice diagnostics, like this progress bar, and also has some nice diagnostics that can show you all the tasks that were run over time. So here we're seeing my 8 cores and what they're working on, and they were doing roughly 400 different pieces over these 3 seconds. We can also see CPU and memory use over the same time. And something interesting to note is that the memory use, this blue line, never actually exceeds around 100 megabytes. So whereas the NumPy version needed to sort of store the entire 4 gigabyte NumPy array in RAM at once, Dask was able to sort of process all this data on the fly and garbage collect fairly aggressively. Okay. I really like this progress bar. I find it really useful for just sort of getting some feedback. So I'm going to paste. That's not what I wanted. So I'm just going to run that all the time, and now whenever I do any Dask computation like this one, I'll have that nice progress bar giving me feedback of when I should expect things to finish. So it's a nice little tip. Okay, Dask Grid does lots of things. It doesn't do some other things. There's Dask Bag. I think I'm going to skip Dask Bag in the interest of time. There's a question in the back? Great. How's this? Is this better? How's this? Is this better? Excellent. Thank you for speaking up.
It's still coming in now. I'm doing an 80%.
How's this? Is that better? Test 1, 2. Check. Check 1, 2. Excellent. I just won't move my neck. So, I can't see you guys then. Okay. Dask Bag is good for handling JSON-like data. There's actually a really cool data set here, which is a lot of inspection of restaurants. And so we have all this gzip to JSON data, and we can look at some of this data, and it's all just this text. It's much more fun if we map JSON loads onto it. And we can see, here's one particular record inside of this big pile of gzip to JSON, and it's showing us some sort of violation of some restaurant. Looks like the restaurant is Early Childhood Academy and Public Charter School. They had some violations. They weren't able to demonstrate some knowledge. So if you're sort of familiar with PySpark or PyTools, the sort of API should look familiar to you. And Dask Bag does lots of JSON-y types of computations. It's very good for sort of the first run of data prep and cleaning. It runs by default on the multiprocessing scheduler because a lot of it tends to be Python heavy. I'm going to totally skip this section to move on to data frames, which tend to be a more interesting topic. We have around 30 minutes left, and so we're wanting to get to those. But it's a really fun data set, some fun exercises in here. I recommend you play with it sort of in your own time, or maybe during other tutorials, because it's great. Okay, so moving right along. Okay, so Dask data frames are, let's get this data out. So just as NumPy was comprised, just as one Dask array was comprised of many NumPy arrays, one Dask data frame is composed of many pandas data frames. Those data frames are separated by an index. So for example, we might have a lot of data sorted by time. We might have one pandas data frame for January, one for March, one for February, one for April, and one Dask data frame will logically sort of coordinate all of those. In the sense that my audio is going in and out again, is that true?
Actually, you can just remove it. Pretty sure everybody.
How's the audio from here? Yeah? Okay. Check 1, 2? No? Not getting anything back. Yeah, okay, I can try that for a bit. Hopefully I just don't need to type. Okay. So Dask data frame implements check 1, 2? No?
There is somebody coming upstairs.
Check 1, 2? A little better maybe? We'll try this for a bit more. If it fails again, we'll trash it. Okay, Dask data frame is very good at anything sort of embarrassingly parallel, like filtering things. It's very good for aggregations, like finding the number of unique elements. It's also very good for anything we do cleverly, so a lot of group by aggregations, a lot of joins, group by apply computations. Things that tend to be a bit slower is we need to do things that require sorting or moving data between lots of the different pandas data frames. But similarly, it runs in parallel. It can run off disk. It's commonly used to interact with 100 gigabytes of CSV data on your laptop. In the next tutorial, we'll also be playing with it on a cluster where it can do some big data things. So here, I have this pile of CSV files that represent, I think somewhere in the UK, and this is where Skipper would have a lot more information. Somewhere in the UK, they measured what people ate and bought food-wise from 1974 to 2000. So some relevant columns. This ST year column is the year, and this min FD column, which is some identifier of some food category. So this data frame is composed of 27 different CSV files in different partitions. So a partition is one of these little sort of blocks of the Dask data frame inside that's a single pandas data frame. When I say a partition, I mean something like this. One pandas data frame might be living on disk or a different computer, but is one of the components of our large Dask data frame. Okay. So by default, we don't really know how our data set is organized because of CSV files. But we happen to know that this STYR column is a special index. How's it going? And so we're going to tell it, okay, this particular column is our index. And now we have known divisions. And so we've sort of told DAS data frame that our data set is indeed divided by year. There's 1 year for every CSV file. And so now our data set is sort of nicely organized by year here. That prep is just going to make a lot of other things nicer for us. For example, we can quickly go ahead and access, say, the data for the year 2000. And DAS data frame now knows exactly into which CSV file to go to pick out a particular data set for this particular range of data. Okay, we're going to switch out mics. Check. Check 1, 2. In the back. We're okay? No? Okay. Are we okay like this? No. Okay. Are we okay if it's more, maybe it's just a reception issue. How are we doing now? Okay, great. My guess is just that the receptor isn't visible if it's in my pocket. Okay, so again, we have a pile of CSV files. And that pile of CSV files is being arranged into many pandas data frames. We're going to lazily load up when we need them. We have one large data frame that's going to load all of them if we need to. So for example, I can compute the length of my data frame. And that's actually loading through all of my CSV files, calling the length in all the individual files, adding up those lengths. And we see there's roughly 8 million rows in this data set. Okay. It's not huge, but this could be larger, it would be fine. So we can ask some questions. We can use sort of normal pandas syntax. Show of hands, who here is comfortable with pandas? Great, that's about 70-80% of the room. So hopefully this code looks familiar to you. We're going to group by this min FD column. We're going to count the number of elements. We're going to find the 10 largest ones and compute that. So we can do that, and DAS data frame has to go and read all the different CSV files, and it produces for us this result. So just like Dask array gave us NumPy syntax on lots of NumPy arrays, DAS data frame gives us pandas syntax on lots of pandas data frames. Functions like DAS data frame reads CSV can sort of allow us to talk to lots of data on disk and load it up each time in case it doesn't fit in RAM. So we saw here that this most popular food was this 401 data set. There's a second piece of data in your data set, this food mapping, which contains what all of these data sets are. So food 401 is liquid milk full price. So the most frequently occurring food that Britons buy is liquid milk full price. So we can sort of join these two data sets and we can get some information out. Okay. So, so your exercise is to find the most consumed food group in 1974, and also the most consumed food group overall. This should be a combination of the code we've seen above, and then a little bit of pandas syntax. You also play with this data. So if you have intuition about how pandas works, a lot of the intuition carries over. So I'd encourage you guys just to start playing with pandas syntax, group by various things, try to see if you can find some interesting content. It's a fun data set to play with, and it's nice to sort of get full pandas-like capability over a data set that is, maybe many CSV files on disk. Okay. I want to walk around. Try things out, see if you have questions. Yes, this does require updating Dask. So pip install Dask. Dash upgrade. 0.11.1.
Can you show them how to run pip from inside the notebook?
Sure.
Okay. So if you were hitting the sorted value error problem, you can try and update your Dask, and it works. It doesn't work in Windows.
That's the thing about working.
Yeah, if you're in Windows, there's a different percent command. CMD. Okay. And after you do this command, what you need to do is you need to restart the kernel because the kernel is still using the old version of Dask. And so you'll have to run a kernel restart. And once you've done that, you'll have the new version of Dask, assuming that it went through correctly.
Which version are supposed to be minimum?
0.11.1. You need the most recent version of Dask for that solution to work. You would type there, see if it has support Dask.
Okay, I'm going to get started again. We have around 6 minutes. So I'm going to sort of finish up this exercise, and then we're going to sort of have some final notes. Again, so there's going to be a tutorial right after this, which is on parallel computing generally. I think there'll be a small section that Aaron will lead on Dask. We'll talk about sort of lots of other options of parallelism, just sort of how to think about algorithms in general, which may be a good complement to this course. I'll also give a course on Dask, talk on Dask on Sunday. All this material is about a year old, so Dask has evolved quite a bit in the last year. There's a lot of new things out there, and Dask is used in other ways than just big data frames and arrays. So it's nice to sort of see those things. So that's my sort of personal plug. I'm just going to skip down here to the bottom. So there's a nice exercise. So you can use this data set to figure out how Britons have been consuming food over time. You may have found that they tend to like milk. But interestingly, the kind of milk they like has changed over time. So there's liquid milk full price, there's other liquid milk full price, and then semi or skimmed milks. So you can see this shift in time, rather for the 1990s, where people become more sort of fat conscious. So it's sort of nice to see that sort of data set come out of this, this analysis, that's a result. Okay, I do apologize also for the bandwidth issues and for the sort of speaker switch. The materials are quite nice. I recommend also going back to the bag stuff if you have time. There's some fun data sets, some fun problems in there. And with that, I think I'm going to finish. If there's any other pressing questions, we'll be around for a while. There's another talk again starting, another tutorial again starting at 10:45 in this same room. We'll have a cluster for you that will have all the data on it. You'll just click a button, you'll get a whole environment for you, so there'll be no setup problems. That might be fairly smooth. So anyway, thank you all for your time. Yeah, great.